Thank you and welcome to my talk about self-labeling electronic shelf labels, pointing the next big thing in retail. So about myself, my name is Steffen Robertz. I'm a security consultant at SEConsult, and this research has been conducted at the SEConsult Vulnerability Lab, where we just get different equipment that they think is interesting, tear it apart, and try to find new vulnerabilities in it. And unfortunately, I'll have to go kind of quickly through the slides because I have a few too many. So in case you have any questions, step by the SEConsult booth later, and I can answer any questions there. So what even is an ESL tag? So an ESL tag usually consists of a display, usually some sort of e-ink display because it's supposed to be low battery powered. It obviously has a battery for this. It's supposed to last multiple years on the storage shelf without you having to touch it ever. Of course, it needs some form of wireless communication because essentially you want to display your price at the tag. So therefore, there's multiple options. Bluetooth Low Energy is an option, NFC, or in our case, it's a 433 megahertz proprietary protocol being used. And then, of course, there's a matching transceiver for a computer, so you can update the prices from your point-of-sale system. On the right-hand side in the picture, you will actually see the base station. This is a base station that's connected to your computer to update the prices. And on the lower left right-hand corner, you can see the sales tag that's being displayed at the store. Right at the product where you buy it. So is it really the next big thing in retail? Well, ESL market right now is supposed to be worth about $855 million, but it's estimated to grow to $5.2 billion in 2032. So therefore, you can kind of see an exponential growth in this market. And it's very convenient for a store owner to switch over to electronic price tags because you can, you can easily change prices without having to ever touch a shelf again. You can just sit at your computer and change it. And at the same time, you can funnel the attention of the customers to a special product where you're offering a promotion on it, because the tags usually have some form of custom interaction with you, because it can blink an LED at you and therefore draw your attention. So here you see some use cases that we saw for the electronic shelf labels. On the top couple pictures, you can kind of see the regular use as a price tag for some apples or for phones. But then there's also some more interesting cases that are less pronounced, but they're still there and obviously have a way greater impact on security. Because for one on the lower left-hand corner, you can see actually the hospital storage unit where they use ESL tags to manage their supplies. And you could see if you could kind of manipulate those tags, you could change out what medication is being used. If someone is not paying close attention, you could potentially grab the wrong medication. At the same time, on the right-hand corner, this is actually a Chinese courtroom where they use the ESL tags to sort their stored court documents. So if you change the contents of the tags, you probably are able to change how the documents are organized, and it would be hard to find the right court documents and therefore prolong court cases or even close cases if essentially proof is missing. So a couple of the attack scenarios we could think about is one, the obvious one. It's we just obstructed the regular retailer and then just blackmail him for some ransom. That's probably way easier to go. Or another option would be you just display some QR code on the tag and offer a special promotion for an item. And a lot of shop customers probably would scan this QR code and actually visit your phishing site in order to get the discount coupon. But then also there's a really cool option for the maker community, because these displays are actually pretty cheap. And as you can see, we will later show how the protocol is organized. So you can just buy these $5 displays and have a 7-inch e-ink display that you can display whatever you want on it. So there's a lot of cases where you could just use it for some hobby projects. So my test server is actually shown on the right-hand corner. We bought some cheap Chinese, very commonly used ESL tags. It uses a base station that's connected via Ethernet to your point-of-sale system or a regular computer in my case. And then the tags connect to the base station via a proprietary 433 megahertz protocol. And our base station is actually the retail flavor, so there's also the industrial flavor, which is a little bit different. Essentially, usually it's just a black box, and it has a couple more LED lights, which is used for the shelf labels in factories. Those tags come in different sizes, so there's like 1.5-inch ones are like the smallest. And then this, for example, is one of the larger ones, it's a 7-inch display. But they're all still pretty cheap and just have a big e-ink display, which is able to display 2 different colors. And then on the attacker side, we just used 2 HackerF software-defined radios because HackerFs are half duplex. So in order to be able to use to send and transmit at the same time, we had to use just 2 in parallel mode. So the design tool that we used, this is actually the regular usage case, is depicted on the right-hand side. You can just use this tool to create pixel graphics, and then you enter pretty much a tag ID on in one of the fields, and you can send it over to the tag, and the tag then just displays your pixel graphic. And one of the cool things is they offer you some customization. So they provide a .NET package that you can just use to integrate into whatever point-of-sale system you're actually developing on your own and offer full support. And we use those source code later for some reverse engineering. So first we start off with the hardware. On the hardware side, the tag on the outside looks pretty basic. So you have the big e-ink display, then just a little LED light, and then on the left is a barcode, and underneath is some hex bytes, which is the tag's ID. When you Dremel the case apart, because it's ultrasonically welded, so if you Dremel it apart, you can see the PCB. And the interesting things here are, one, the RGB LED, and then marked in orange, it's the SOC being used. It was just labeled eTag M1, and we could not find any information about the SOC whatsoever. In red is marked the flash memory. It's the regular SPI flash memory, so we were able to connect to it and dump it. On the right-hand side, in yellow, there is the RF module, which just was labeled with this random number, and we also could not find any information about this, and unfortunately also did not find anything out after delayering it. On the back-end side, the PCB is pretty bare, so you can just see the battery connectors, and then there was a debug header, or at least that's what it looked like in the beginning, and I'll talk about that a little bit more later. So first, I just started by dumping the SPI flash memory because that's kind of the easiest thing. It's a supported flash memory by flash ROM, so you just hook up to the 8 pins and then dump it. It has 2 MB of storage, and you could see that when you render the data, you could see that there was the image data actually stored at address 0x1E1000, which is just the black color channel first, and then the red color channel, and the image is pretty much just stored in rows, so you just go through the display, and a 1 just means it's black, and a 0 means it's off. So just by going through the display, you could have a bit stream, and that bit stream was there. But the beginning of the flash also was something else. It was consistent across all ESL tags, and the entropy was kind of low, between like 0.6, 0.8. So we believe that might be actually the firmware for this unknown microcontroller. And then I just created some simple Python scripts in the beginning to render the image data and try to play around with that. But it didn't really lead us anywhere besides that you can now take memory dumps and analyze what's being displayed. So next we tried to identify the eTag M1, since that was kind of the interesting part. Usually how we go about this is we just use our multimeter and kind of try to trace out what pin connects to where. Because we were hoping that we could find a schematic of a custom or a very common microcontroller that would kind of fit to like the VCC and ground pins or oscillating pins, because usually you can't really choose those. They're fixed in position and they're very easy to identify. So that's the schematic we came up with of what pin connects to what. But unfortunately, we couldn't find any matches to this microcontroller. So in order to to try and identify it, I decided to boil the chip in 95% concentrated sulfuric acid. This will remove the epoxy packaging, so the black stuff that you could see in the earlier pictures. And now we can actually see the silicium dye, kind of in this golden color on the right-hand side, where the edges are kind of missing because I use metal tweezers, and metal tweezers are not good with silicium because it will just chip. And after that, you just clean it off with some alcohol, and after that, you can try and use a microscope to look for some identifying marks on the chip. So luckily, on one of the edges that didn't chip off was actually the edge where it was marked. So here you can see the logo of ST Microelectronics. So now we know this chip is definitely manufactured by ST Microelectronics. The 2010 marking likely indicates that it was designed or produced in 2010. And then there's some probably internal STM part number that we were not able to trace, but someone at ST is probably able to know what design this actually is. So once we knew that it's ST, we kind of only have two big options left. It's usually STM32s or STM8s, because those are the only like common lines produced by STM. So next, I had to look at the debug header on the backside of the PCB. It was 4 pins. Pin 1 mapped to the microcontroller's pin 2. Pin 2 was ground. Pin 3 was microcontroller's pin 1. And pin 4 mapped to VDD, so the voltage line. So this seemed kind of familiar, and having a look at the data sheets, I noted that on the right-hand side you can see the SWIM connector. It's STM8's proprietary debug protocol. And you can see that it kind of looks very similar. It has VDD, it has ground in between, and then the data and the reset line. So it kind of looked like my pinout, just that pin 1 was marked in the wrong direction. So it just flipped around where they marked their pin 1, and pin 1 is actually pin 4. So this would leave us with pin 1 on the PCB being reset and pin 3 on the PCB being data. And I just confirmed this by pulling the reset pin low and seeing if the tag would actually restart, and it did. So therefore, reset was known, VCC, ground was known, so it was very common in the sense that data was next. I then used the HCM flash tool with an ST-Link V2 in order to debug the memory. And I just decided to try and dump the memory. However, since we didn't know the exact module, I just used the largest module I could find in the tool, which was the STM8 S2081B. And all the STM8s have the same flash layout. Therefore, we knew where the flash, actually the code is being stored and where the ROM is stored. So then I just decided to dump the flash memory. However, when I dumped it, you can see on the right-hand side, all that came back are 0x71. And that didn't really look like anything impressive. However, looking at the STM8 forums, you could tell that reading 0x71 usually indicates that the readout protection is enabled. So actually they did something right and enabled the security measures so you can't read out the flash memory. However, we are still able to derive some information from this, because you can see that the flash ends at 0x1000, which shows us that our chip only has 64 kilobytes of flash and not the 128 kilobytes that the flash module has that are used in the parameter. Therefore, now we have an STM8 with 64 kilobytes of flash, and I just did the same for the EEPROM area, and I was able to derive that we have about 2 kilobytes of EEPROM. So now we have some more identifying marks about this chip, and we're able to use the ST database to look for some chips that are an STM8 with those properties. However, we still couldn't find the right chip that would match our pinout. So I dug a little deeper, and unfortunately there's nothing like a chip ID in this sense, but there is a unique ID. So there's multiple addresses known for STM8s that are being used for unique IDs, usually it's just those 3. And on the right-hand side, you can see the table, how the unique ID is being parsed. So it consists of a lot number, a wafer number, and a X and Y coordinate on the wafer to make it a unique identifier. So reading through all those 3 addresses, I was only able to find one address where the data would actually fit the scheme depicted in the table. So my chip actually has a X coordinate of 31, a Y coordinate of 58, was wafer number 2 in lot number G904379, and thus is now fully identifiable, at least for ST, because they claim that they can trace any chip through the lot numbers. We reached out to STM, however, they did never answer to us back about what actual model is being used. So we couldn't really get any deeper than that, but the address indicates that it's an STM8L series, which would make sense because that's the STM8 low power series, which just fits the application. Then we did also some OSINT, because we still couldn't find a chip that matches the pinout that we found. So we bought the ESL tags through Alibaba, and the factory is actually an Alibaba Gold Plus supplier, what that means is that you get a really nice report by Alibaba, so by a third party, where they check out their production lines and give you a full report of what machines they own and how good those machines still are and how much years of usage you can still get out of them. And this list contained ultrasonic fuse, which led us to believe that maybe the STM8Ls are actually custom bonded, so therefore have a non-matching pinout to the regular one. And that doesn't really matter because we found out the lot number, so it should still be traceable now. However, a different opinion would also be that the ultrasonic fuse is just a bad Chinese translation for ultrasonic welding. So that was used for the plastic case. So we still don't really know, but it would be cool if it has a unique pinout. So next, I had a look at the RF protocol. So the first thing you kind of do with the RF protocols, you just ask the vendor or see if there's an FCC ID somewhere printed on the case. In our case, the vendor told us the FCC IDs for the base station and for the tags, and I pulled down the FCC files, and you can see some interesting information about the RF information. So you could see that in orange, the frequency range of the base station and of the ESL tag is marked, and also the modulation type. So one is the Gaussian frequency shift keying, the other one is an amplitude shift keying. And kind of looking at this, we're just like, this doesn't really make sense, because why should a base station have a different modulation than the tag, but they communicate together? It just doesn't seem right. So also the FCC listed this at 433.92 megahertz, and the manual talks about it having some frequency hopping technology for anti-jamming, which also seems very fishy because they only claim one frequency, and if you use frequency hopping, you can't just stick at one frequency. So something about these FCC filing is just really off. So I decided we can't really trust any of those FCC information anymore, and they're probably faked, or I don't know, knew someone at the lab. So we just had a regular graph run and checked where the most frequency amplitude was, which was more at 433.254 megahertz. So also that information on the FCC files is somewhat wrong at least, and it's a little offset here. And we were able to see some data being transmitted here. So I thought, what's the easiest case we could try right now? And that's usually a replay attack. So in a replay attack, you just decide to capture all these RF samples and replay it at a later time and see if the same action is performed again. And that's just what we did with the hack RF. So I just captured all the samples, and on the right-hand side, you can see the store owner. He just changes his price to $5. And on the lower side, you now see the tag. And in a little, it will display the new price of $5. And it will always take a little while to refresh. But then the price is being shown. So the next day, you can imagine the store owner wants to change his price. He wants to make a little more profit. So he just changes his price to, let's say, $7. And he will just send this price over again to the tag. And then after a little while, the tag will receive the information and the new price will be displayed here. So now the customer will have to pay $7 for the same item that was $5 last day. So as an attacker, we'll think, oh, $7 is kind of bad. If we recorded the samples for $5, why can't we just replay the $5 and see if we can change our price back to a $5 per item? So I just used the same file that I saved before with the RF samples, just change one parameter from receive to transmit, and send it over again. And then you can see the price changed back down to $5. So this definitely indicates that there's no elaborate security scheme implemented here. And you can just replay pre-recorded messages to repeat the action. But then I thought, let's have a closer look at the RF protocol, because replay attacks are cool, but you still need to have captured the price tag before. So since we didn't know the correct modulation, I just decided to figure it out first, since that's kind of essential to capturing traffic. So here you can see a waveform graph. The color is actually the intensity of a frequency. On the right-hand side, on the x-axis, you have the time, and on the y-axis, you have the frequency offset. And you can see the little red lines in here that kind of shift between zero frequency and then a positive offset and a negative offset. So that indicates that FCK is being used, so frequency shift keying, because we encode information in a shift of frequency. So I decided to first start manually decoding the frames because we still have no idea about symbol rates or anything like that. I used the tool in Spectrum. It's pretty cool to use because you just load your dump file in it, and then you can just right-click and add a derived plot, for example, for frequency if you have a FSK scheme. Then you get the middle graph, and then on the middle graph you can just add another derived plot of threshold, and that will give you a bit stream. And then you can just add those little markers to the frequencies, and it will tell you what symbol rate you are using, and you can just copy those bit streams and then have a look at the bits. So I did this, and I identified a couple of different messages. So first, the tag is sleeping. In order to change the price, you have to wake the tag up. This is made so the tag obviously saves power. The base station does this by sending 920 frames, since there's no elaborate scheme of knowing if a frame did not arrive correctly. Actually, the base station will just send this frame 5 times each. So instead of 920 different frames, you're actually sending about 4,000 something frames. And those frames are being transmitted at 175 kilobaud. And it just consists of preamble of AAA, which is kind of the default for RF systems, a synchronization header, so you know if you're synced right to the frame, then the frame length in bytes, the tag ID, obviously, which is the code that's being printed on the tag, a fixed value, which was always 0 for me, then a frame counter. This is just the counter of 920 that counts down depending on what frame you're at, a fixed value of 0A, and then a CRC16 about everything starting with a tag ID. Next, we have the image frame structure, which is the first frame that actually consists some image data. This image frame is sent at a different frequency, a different baud rate of 100 kilobaud, and it has frame 1 out of 9 and some image data, and I have to hurry up a lot because time is almost over. Then there's some special image frames, which is used for the larger tags because the older ones only can contain 256 different frames, and that's not enough for the large tags. So they just added a kind of added-in frame that handles those. Then there's the actual image data structure, which has a compression header and then a compressed image data. There are 3 colors supported on the tag, white, black, and red. So you need at least 2 bits per pixel. And I could tell from the image captures that some sort of compression was being used in order to do this. And it was run length encoding, which I did by reverse engineering the SDK package that they provided. So run length encoding, you just use a bit stream and see if there's, for example, 8 zeros in a row. You can compress them to a 1 and then an indication of how many ones are in a row. And those are the 4 different cases that you have here. And then the tag just responds with some information as well, which is also just the battery voltage and some signal indicator and the temperature. So knowing all of this, I built a GNU radio sketch to receive the image data and to render it out into a picture, which is then played here. So on the top end, I'll run the GNU radio sketch, which is this, and I'll just have in the background. It will forward on the image data that I receive on the ARF interface to a Python script over a UDP port. And the UDP port and the Python script will then just interpret the data and render it, so you can see all the image data is received, and the image is rendered into a picture again on your browser, in your screen. So you actually have you can actually now fully understand the protocol and see all the image data. So since we fully understand the protocol and we didn't see any indication of a password or some encryption or authentication, we can also just write our own. So I wrote a blog, which is called the image source blog in GNU Radio, that will wake up a tag where you give the ID from, and we'll use a picture to send it over to the tag. And then we just have the FER filter, which is used for GFSK, so that's just the Gaussian frequency shift keying together with the frequency shift keying block in order to have a filtered output, and we just pipe that over to the HackRF. And doing this, we send it over now. All the frames are being generated first, also wake-up frames. Those are the actually data frames of the picture. And then on the right-hand side on the multimeter, you can see the tag wakes up and starts to draw some power. All the user being displayed because obviously all our data was sent already. And then on the right-hand side on the tag, you can see our company logo being displayed now. And all we had to know for this was the tag's ID, and that's it. And after the tag is refreshed, you can see it going back into sleep mode and the power drops back down. So in conclusion, we identified the unknown microcontroller. We gained access via a debug port. We then confirmed the replay vulnerability and used this as an indicator that the tag is actually vulnerable. So we reverse engineered the RF protocol and gained the ability to send and receive valid frames and are now able to decode any price update or change any tag information. And kind of cool thing about this as well is that the range is only limited by the RF power, since we don't need any answer from the tag. Therefore, the actually will scale for distance. If you stand further outside from a supermarket and you stand above the legal RF power limits, you're still able to change the tags. So the lessons learned is just because you use a proprietary protocol doesn't really mean you have a security measure in place. It just means it's harder for a security researcher to do his job and have a look at the protocol. However, once you decode the protocol, a very cheap Texas Instrument RF chip for like $2 will be able to speak this protocol, and you'll be able to change any tag you see. Also, the protocol robustness could have been improved greatly, which probably would have saved some more power, which kind of shows just shitty engineering in here. Yeah, and relabeling a microcontroller also just does not protect you against finding out, because the die still has some information on it, and debug access still gives us some information. And all the codes and stuff will be released on GitHub. However, we're still having some licensing issues here. But it will be released in the future, so everybody can play around with the ESL tags and buy their own from AliExpress. Thank you.
Thank you very much, Steffen. And I think we have time for one question. So is there a question from the audience? Okay, no question so far. Oh yeah, there we have a question. Okay. Just a second, we'll provide you a microphone.
Is there any value in this? Like, what's the use case for it? You can change all the tags, but does it provide anything?
Well, like I said in the beginning, it has the regular price tags, probably not that interesting, besides blackmailing a store, for example. However, we saw it being used in power grid storage facilities, and you could kind of see power like parts being rated for different amperage, and them all looking kind of the same. So if you switch out the tag information on them, you could probably not distinguish which part it is, and somebody would put in wrong parts into a power grid, which could break critical infrastructure, but it's a lot more edge case.
So let's thank the speaker once again. Thank you, Steffen.
Thanks.